Outpouring physics. That's right. Pick up these orders.
Oh, so it's like an hour after this one. How you doing?
No,
Answer the questions.
Okay, today I'd like to cover, actually, it was something that seems to be a struggle for a number of you. It's not a new topic at this point, but it's a struggle. And so this is going to be related to the lab this week. Let's see if we can calculate the normal force on the hinge of that bar, okay? And then this is an example of adding up forces and setting the resulting to zero. It seems that people are still struggling maybe with adding vectors. That was one of the things that came out on the last exam. So we're going to try and focus on this for just a little bit, just to get it all narrowed down. The next topic is momentum, and that has more vector additions. Okay. So, on the lab this week, if you're trying to do the analysis for this lab, let's say you have the little arm, you had a spring, say you had a distance R1 from the suspension, from the pivot point, and let's say it just moves out at an angle theta. A little bit further down this rod, you have the mass of the arm times G going downwards. And then you have a hanging mass hanging off of that, and that exerts a force, mass of hanging mass times G. Like here, let's call this distance R2, this distance R3. Okay? Is it clear what kind of the setup is? We'll call this the tension force. And so one of the questions is, well, first of all, the main question was, what's this tension force? Second part of the question was, what's the force on this pivot point, on the elbow joint, so to speak, if this was considered to be an arc? And so I want to kind of consider the second one in terms of the magnitude of the tension force. By the way, how do you get the tension force?
You set up the torques.
Yeah.
Set them equal to 0 and then.
Is everyone comfortable with doing that? Okay. So we're going to suppose that we know the magnitude of the tension force. No, magnitude of tension force and that angle. All right, now if I wanted to get the force on this joint, what should I do?
The y component of the tension force and added to the two forces that are down and set it equal to 0.
Well, yeah, so
The y in there.
first of all, let's draw where the force would be here. Which way do you think it would go? Let's see if we can just draw this force. So if I drew the force like this, is that a possible force?
No,
Why not?
it's not against the. It goes along with the tension force and it shouldn't.
So this is in static equilibrium. What that means is it's not accelerating or rotating. if I look at these forces, there are two forces that have parts in the along the x direction, right?
Mhm.
This tension force has a part in the, going that way. And
Negative.
if I drew the normal force having a part going that way, it should be accelerating that way,
Yeah.
right? Makes
Yeah.
sense?
It has to be perpendicular to your tension line.
No.
Well, it may not be perpendicular, but it definitely has to have a
Counter.
component that'll balance the part of the tension going that way. Okay?
Mhm.
So I'm going to draw it, I mean, you can draw it any way you want. I just want to draw it so I can introduce an angle. I'm going to just draw it like this, okay? And I'm going to call this angle, what should I call it?
Alpha. Or,
Okay, alpha works. I like alpha as an angle, so. So we can draw it that way. If alpha turns out to be negative, it actually meant that the normal force was down like this, okay? Which is probably what it will be. Yes.
what if it didn't?
What's that?
What if it didn't turn out?
If it's positive, then yeah, then it's this way.
Oh,
Well, but the way it is, wouldn't it have to be negative? Because it's got to balance the tension force?
And also these M's.
Yeah. Oh, so it depends on your mass.
Well, actually, you're right, it does have to, the vertical component of the tension force, the torque that balances these. And since these are further out, the tension force actually has to be bigger than these ones. So you will see that the normal force actually should be probably downwards. Okay, let's look. With that argument, we'll go ahead and draw it, just to avoid confusion. So we'll call this theta. The normal force will point the normal force downwards. Okay? We'll call this angle alpha. So I'm going to redraw things. I'm not going to worry about the tension, about these distances, because they're good for torques. I'm just going to draw a free body diagram now. So if I draw a free body diagram, I have tension going upwards, with an angle theta. I have normal force going downwards. I have MG, MAG going like this. And I have MHG going like that too. Notice I didn't draw any of I just drew the forces. The total forces on this have to balance. So if I'm not worried about torques, I'm not worried where they're applied. Does that make sense? So what do I have to do if I want to figure out that normal force?
How to follow the forces in the y direction and the x direction.
That's right. The condition to figure out those forces on the hinges is that the sum of all the forces is going to be 0 because it's not accelerating. And so I have to find all these forces and then write out all these forces and then add them up. That's alpha, right?
Mhm.
That's a different angle as theta?
What's that?
Is a different angle than theta?
Yeah. Potentially. Okay, so what should we do?
So the sum of the,
Use X components. to Y
Yeah.
components.
Yeah, so if the sum of all the forces is 0, that means the sum of all the forces in the x direction is 0, and the sum of all the forces in the y direction is 0. So now I need to find all the parts of the forces in the x direction, right?
mhm.
So I'm going to introduce coordinate system, x, y, like that. What's the x component of tension?
It's gonna be the R1.
Why does it involve r?
That is
Just T.
X component of tension is going
Magnitude
One
cosine.
What's that? Okay, so magnitude of
T times
Cosine of theta.
R sine of theta? No, or not.
why is R
Oh,
coming
okay,
in?
never mind. Never mind. That's for the first part.
That's for, yeah, that's for
Yeah.
the torque, yeah.
It's gonna be tension cosine of theta.
That, well, yeah, so this length here is T
Cosine?
cosine of theta. And does this point in the positive or negative x direction?
Negative x direction.
Yeah, because if x is going this way, so I have to add in that negative sign by hand. So negative T cosine of theta. Make sense?
Mm-hmm.
How about the normal force? The part of the normal force that points in the x
It's
direction.
gonna be positive and alpha. Yep.
Yeah, cosine of alpha.
Cosine of alpha. Okay. So this means that, and that's it, is there any other forces in the x direction?
Mm-mm.
Good. So that means that normal cosine of alpha minus magnitude of tension cosine of theta is equal to 0. Okay, there's one equation. All right, how about the y direction? What are the forces in the y direction?
Now it's gonna be sine of theta side of theta. Tension sine of theta.
Okay, tension sine of theta. You see that? That's the part of the tension force pointing in the, this is T sine of theta. Minus
Minus MAG.
MAG, good. The mass of the arm times G.
Mm-hmm. And then minus MH.
Mass of the hanging mass, G, good. Was that it?
Minus n sine of alpha.
Minus,
Yeah. And
minus n sine of alpha. Follow that?
yeah.
Where's the sign of alpha come?
So this is my normal force.
Oh,
This is the part of the normal force in the y direction. It points in the negative y direction because it's downwards. And if this is magnitude of the normal force, then this side here, the opposite side of that angle, would be magnitude of the normal force, sine of that angle. Okay?
How do we know that the normal force is going down?
Well, we're not 100% sure. If we get a negative alpha, well, I'm 100% sure, but I mean, if we have a negative alpha, it would have been going upwards. Here's the argument that I had for it to be going downwards. The vertical component of tension force here, and these two components of, and these two weight forces, the two of these have to balance. And since these forces are further out from the pivot point, there'll be smaller forces than the vertical component of tension force here. So the y component of tension force will be bigger than the sum of these two forces. And that means that the normal force to balance it would have to be pointing downwards. But you have to kind of think about that for a little while. Just draw the force and draw an angle. And then if the angle turns out to be negative, then you know it's downwards, okay? All right, so what do we do now? Now we have two equations. Two equations, and we don't know, what don't we know? We know everything, the normal force, and we don't know what the angle is.
So on the top one, solve for the n cosine of alpha, like set it
Okay.
equal to, and then sub it in. No, you can't sub it in.
Yeah, we could do something like this, right?
Mhm.
There's a bunch of ways to do this. Unfortunately, when we're adding up vectors, we usually have two equations, for x and, equation for x, equation for y. And so the algebra gets a little bit complicated. Here, what should I do? If I'm going to solve for this. Maybe I'll solve for this
Yeah.
and substitute it into here, and then I'll be able to get that angle.
Yeah.
That's one way to do it. Alternatively, I could solve for the angle, substitute that into here, and then just have an equation for normal for the.
How do you solve for one when you don't know both of them though?
Well, let's go ahead and do this.
Okay.
We know what the tension is, right?
Yeah.
Let's assume. So we say that the normal force cosine of alpha is equal to the magnitude of the tension cosine of theta. Right? So the normal force is equal to the tension force cosine of theta divided by cosine of alpha. Let's take this expression for n and plug it into here. So I would get 0 is equal to t sine of theta minus m a g. I'm just going to write minus ma plus mh g, okay? Just combine two terms. Minus normal force sine of alpha, and I'm going to write the normal force as tension sine of theta, or cosine of theta, over cosine of alpha times sine of alpha. And that's it, right? This sine over cosine of alpha, so I can do that, right? What's this?
Tangent.
Tangent of alpha, right? So I would get tangent sine of alpha, or sine of theta, minus ma plus mh g, minus tangent cosine of alpha, not cosine of theta, tangent of alpha is equal to 0. For this first part, let's just figure out what this alpha is, okay? So I'm going to bring this over to this side. And then, so I get tension cosine of theta, tangent of alpha, is equal to tension sine of theta minus ma plus mh g. I'll divide through by tension cosine of theta. So these cancel. These two tensions cancel, and I'm left with sine of theta over cosine of theta, so it's tangent of theta. And nothing cancels here. So I get tangent of alpha is equal to tangent of theta minus ma plus mh g over t cosine of theta, and that's magnitude of tension. So what would I do if I wanted that angle?
Then divide by, oh,
Oh, yeah. I'm gonna write, I don't need this anymore.
do you take arctan of the other side?
Yeah, that's right. So alpha arctan of the tangent of theta minus mr plus mh g over t cosine of theta. Okay, so that's your angle. It's kind of a pain, isn't it?
Well, that's because we have two unknowns, right?
Yeah.
Yeah, we have, so you need two equations.
Yep. So this is the angle. Once we have the angle, we're pretty much set. We can easily figure out the magnitude of the normal force back from this. So magnitude of the normal force is just the tension cosine of theta divided by cosine of alpha. So So once you know alpha, you just plug it into here since you know everything else. And you're good. And then you could get the x and y components, knowing that, you know, in x.
So
Yeah,
the force of the spring is the same thing as the tension force,
yeah,
right?
that's right.
What were you gonna
So
say?
do we have to compare, we got two different forces for the spring. We did like the calculated one that we did based on our measurements, and then we
Yeah.
also did one based on the hanging the mass from the thing. Do we do it for both of those different ones?
No, so the first part, you do everything based on the calculated spring,
Okay.
based on the torque, balancing the torques.
Okay, so we'll use the calculated one
Yeah.
for this part.
Go ahead.
Because the only reason you did the second one is just to check.
Check and make sure it was within
Yeah.
15%. Okay.
You guys want to do another force balancing one? We have to look up another tension one?
Sure.
All right. This is another statics problem. So, I promised Ellen we'd do this problem. Let's say I have a tight string that's suspended between 2 points. And let's say the length of this is L. And let's say that I want to, braking strength might be, let's say braking strength is 1,000 newtons, or 10,000 newtons, like 1,000, like 1 ton. Now you might think that that'd be pretty impossible to break by hand, by a person by hand, right? Turns out that you can do it. What you do is if you have two points that are pretty tight here, let's see what the force. Let's see what the tension force will be if I pull on the middle. So if I start pulling on the middle, these things deflect a little bit. So I'm going to say T1, T1 here. I'm going to look at this central point, and then let's say that the tension applied. I'm going to call this the force that a person applies to the middle. Let's say that this distance was D, that it moved down in. And L, let's say L is 2 meters. D is about 2 centimeters. I guess it'd probably be more. Let's do 10. Let's do 10 centimeters.
Would L decrease once you start putting pressure on the board?
Well, we're assuming that these points are fixed, you know, maybe between 2 really tough walls or something like that. Or,
Okay.
but does it make sense what the problem is?
Uh-huh.
All right, here's another situation where if I can draw a free body diagram for the point right here. What's the sum of forces on that point have to be?
0.
0, right? And so I can add up forces and just see, you know, what the forces have to be in order for it to be 0. Now, I want this tension, the magnitude of these tension forces, if I want to break it, I want it to get up to 10,000 newtons. I want to see what this applied force has to be. Okay, make sense? So let's go ahead and see if we can do that. First of all, I can figure out this angle here, can't I? when I pull on it, this is 1 meter, this is 10 centimeters. So what would this angle be? How did I get, is it clear what the problem is?
It's the tangent of 10 centimeters over 1 meter.
Mm-hmm.
Okay.
Yeah.
So tangent, arctangent?
Arctangent of.
Yeah, okay. So theta is arctangent, or inverse tangent, of 10 centimeters over 1 meter. What's that? 0.1, isn't it? Do you follow? Arctangent of E over L over 2. So this is L over 2, this is D. Theta is arctangent of D over L over 2. Okay. Plug in numbers and it's that. What is that number?
Mm-hmm.
Okay, 5.7 degrees. All right. Well, let's go ahead and sum up all the forces on this point here where I'm pulling on it. So what are the sum of the forces in the x direction? By the way, this angle here is same thing if I pull in the middle of that string. What's the sum of forces in the x direction? That has to be 0, right?
Mm-hmm.
Is that applied in the x direction at all? Well, let's define our direction.
No.
So what are the forces on that point in the x direction?
So like the tension,
It can just be 2 times the
So I have 2 tensions, right, going out from that point. If I draw that point. If I draw it just more clear, T going that way, T going that way, one, well, 2 tensions going that way, and then force going down. So I just get T
cosine of theta.
cosine of theta minus T cosine of theta, right?
Uh-huh.
With 0. Now let's look at the sum of forces in the y direction. That has to equal 0 too if it's not accelerating.
Mm-hmm. T sine of theta minus
Good.
T times.
T sine of theta from one of these.
Mm-hmm.
So so this is theta, that means this is theta. Okay.
Plus T sine of theta.
So this side would be T sine of theta. And I get the same thing on the other side, right?
Yep.
So 2T sine of theta, good. Minus that force that I applied. I'm just gonna write it like that. And that's equal to 0, isn't it?
Mm-hmm.
So F is gonna be 2T sine of theta. And if I want if this T is 10,000 pounds, or 10,000 newtons, theta is 5 degrees, 5.7 degrees, what would this be?
Wait, T is 1,000.
T is the 10,000 newtons if
10,000.
I wanted to break it.
So wouldn't you take half of that?
What's that?
Would you take half of that?
I'd do 2T times 10,000. No, I wouldn't.
1,986.
Yeah, I just need the tension to be 10,000.
So is it 1,986? Point
Sine of theta would,
5.7.
5.7?
and what's that equal to?
1,986.4.
986.
1,986.4 newtons, which is about the weight of
$200 kilograms times G roughly.
And so that's a heavy, that's hard to pull it, but that's not unreasonable for a person to exert that amount of force quickly.
So you have to be 200 kilograms.
No, I mean, if you tug on it quickly, you can probably, I mean, that's not unreasonable to get up to that. And so what would happen, so that 1 ton braking strength, a person, if you made it tight, it would, because, by the way, steel cable's different. You probably are getting more like 0.05 for steel cable, or even less. In which case, you would basically have this. Okay? If you had less, if you had half that inch. What do they say about steel cable? What do they say about
So it's been a good time to get that.
We have Mr. Springs.
Were you working on earlier? Is that where you were trying to course on the joint, right? So when you were in your office, this one, it's not that way?
Yep, it's that way too. All the way through. There's many ways to do the same.
I was like, I don't even have my laptop.
No, this works fine.
Okay.
There's many ways to solve it.
Okay.
So this is.
I'm not worrying about it.
Thank you.
How do you
I was
use
freaking out a little bit.
Yeah, don't worry about it.
Okay.
I'm okay with it.
Yeah.
Yeah.
As long as you do it correct,
Yeah.
the horses.
Yeah. Exactly.
Thank you.
Sorry.